So hello, everyone, and thanks for joining this, our latest episode in our global webinar series. My name is Wilmer Companioni, and I lead the technical marketing team at KEMET. And I will play a little bit of double duty today. I'll be both your host and your presenter for today's webinar. So a little bit about myself. Like I said, I lead the technical marketing team at KEMET. I've been with KEMET now for 6+ years, and I have a total of 14 years of industry experience. The reason some of those numbers don't add up is for a number of those years, I played a little bit of double duty, but I started in engineering design. And as I said, 6 years with KEMET and 2 years with sales, in sales. The topic today, we'll start with a really high level view of MLCCs. If you're interested in some more details about MLCCs, we actually hosted a webinar on this topic a few months ago that you can find in our library of past webinars. But today we'll get into also what all those alphanumeric C0G, X7R, X5R designations even mean. And then we'll get a little bit into the materials, right? MLCCs are obviously multi-layer ceramic capacitors, but they're not all made with the same materials. And those variations in materials have differences in its effects over time, temperature, and of course, piezoelectric effects. And time permitting, and I believe we will have time for a Q&A session. So MLCCs come in many different shapes and sizes. Most of us, definitely the last 20+ years of electronics or more, mostly use the surface mount variety, but even the many of the leaded types are actually internally also of the MLCC type. Internally, they just happen to have a lead or lead frames on them as well. And multi-layer ceramic capacitors are exactly that. They are alternating layers of a conductive material, is what the so-called electrode plates are made out of, separated by a ceramic dielectric body. And there's some variations there, obviously, in the options that you have available for the ceramic dielectrics, as well as the internal electrode structure. That comes in two flavors, so-called BME, which stands for base metal electrode, which is oftentimes nickel, and then PME, or precious metal electrodes, which can be silver, palladium. PME variations oftentimes require the use of lead in the manufacturing process, and therefore they're not RoHS compliant. But the far and away the most popular type is the BME type. So continuing along with this whole alphabet soup of letters and numbers that we throw at you when it comes to ceramic capacitors, we have them available in all these variations. Now, those numbers and letters mean different things, and we'll get into what some of that means. But when somebody says X8G, C0G, U2J, those are your so-called class 1 ceramics. And then when you have X8R, X7R, X5R, those are class 2s. And then finally, we have class 3s, the Y5Es and the Y5Us. And all those letters and numbers basically try to tell you the capacitors, the ceramic capacitors, performance over temperature. So how much capacitance change you can expect over temperature. So class 1 ceramic capacitors are made out of a material known as calcium zirconate. Calcium zirconate is a very stable dielectric. As you can see there, C0G and U2J have really little to no variations on capacitance over temperature. We have recently introduced a new dielectric material type known as X8G. It's also a class 1 ceramic material, extended temperatures up to 150, and its capacitance over temperature performance is very flat. U2J has about, I think, 2 to 3 times the dielectric constant of C0G, but it has a very ever so slight variation of capacitance over temperature. And then we get into some of the class 2 types. Now, both of those are made out of barium titanate. Now, I'll get into a little bit of why it is that they have different dielectric constants if they're made out of the same material. This is one of the questions that I had early on when I was learning about ceramic capacitors as to, well, if they're made out of the same material, why is the dielectric constant different? So we'll get into some of that later, and a little bit later into this slide. But as you can see, while X5R, X7R, these class 2 ceramic capacitors have much higher dielectric constants than your class 1 variety, or those made out of calcium zirconate, they don't quite have the same temperature stability. Now, this temperature stability is comparatively pretty good when you start looking at your class 3s, and those are your Y5Vs and Z5Us. Now, once in those class 3s, you get a lot of capacitance, but once you deviate from room temperature, even just a little bit, their capacitance really starts to change quite a bit. Now, that's not to say they're not common or they're not used. They're actually extremely common, but more often used in throwaway electronics. I tend to make the analogy of like the toys you get at McDonald's or the fast food restaurants. Those are more like your Y5V, Z5U type capacitors that generally these devices are not going to experience a lot of temperature variation beyond room temperature. So you get a lot of capacitance in a very small package, but of course you sacrifice the stability. Now, as you can see, if you kind of pay close attention to this graph, they're all made, as I said, of the same barium titanate material, but why the big variation in dielectric constant? And that's where sort of the secret of dielectric formulation comes in. Now, while they are all barium titanate, what capacitor manufacturers do is that we add some dopants to the material that effectively flatten out and widen out this curve. So you can almost think of it like an integral problem area under the curve type of thing, where these dopants that has some variation from capacitor manufacturers to another, these dopants that we add actually flatten and widen out that curve in that material so that you can get that temperature for performance that you see in X5R and X7R. So almost imagine, it's not quite 100% true, but imagine as though Y5V, Z5U is almost undoped barium titanate. And then if you want to get better performance out of that material, you add these dopants that cause the capacitance peak to come down, but of course it widens out and it becomes much more stable across temperature. So what do all these letters and numbers mean? Well, what the letters and numbers mean actually varies somewhat. It varies whether it's a class 1, class 2, or really even class 3. Now, per EIA, this is the standards body that we all capacitor manufacturers follow, defines what the performance of a capacitor should be over temperature. So in the case of C0G, the first letter C stands for the first significant figure of the coefficient, the temperature coefficient in terms of parts per million per degree C. The second, the numerical symbol, is a multiplier to it. And then the last symbol is basically the tolerance of the temperature coefficient. So if you look at C0G, that basically means it has -30 ppm per degree C across the range of -55 to 125. And that part is important. This designation is accurate for the range from -55 to 125. The other type of class 1 capacitor that we offer is a U2J. Now those U2Js, again, we're looking at the range from -55 to 125, and that means it's the first letter is 7.5 times -100, and then that's the tolerance is plus or minus 120 ppm. So that's what it's going to be. So it's still very stable, right? We're talking about a couple of, maybe a couple of thousand parts per million across the temperature range from -55 to 125 for U2J. So still very, very stable. Now, this whole alphanumeric decoder ring changes a little bit when you start looking at class 2 and 3 dielectrics. In this term, in class 2 and 3, what it actually tells you is the low temperature, the high temperature, and then the maximum allowable cap change over that temperature range. So in the case of X7R, the X stands for -55, the 7 stands for 125, and then the R stands for plus or minus 15% across that range of -55 to 125. Now, plus or minus, I would say, is perhaps a little bit generous. It's actually almost always minus. So think of it this way, back to that table that I showed earlier with the magnitude of dielectric constant over temperature. As you deviate from room temperature, you kind of go down from that peak. So it's always minus in that ppm range. In the case of X5R, so the X still remains minus 55. The 5 means 85 degrees, and then of course the R, the last R, then again means plus or minus 15%. Now, we have recently introduced, as I said, X8G. So according to this table, which now kind of becomes a little bit of a hybrid between the class 1 table and this class 2-3 table. But anyway, in the case of X8G, it actually means from -55 to 150 degrees with plus or minus 30 ppm per degree C. So really very wide temperature range and very, very stable. And that's X8G is considered a class 1 dielectric. So what's going on internally? If you look at the internal structure, the crystalline, the microcrystal structure of class 2 and 3 ceramic capacitors, you actually have in the crystalline lattice your barium, oxygen, and titanium in this, with the titanium in the center in this face center cubic structure. Now, if you know anything about the periodic table, titanium is actually a big fat atom. And when the ceramic body is first comes out of the oven, that cube is pretty well relaxed, and think of it as though it's expanded enough to the point where that titanium atom can comfortably sit in the center of that crystalline lattice. But as it cools down and you fall below that Curie point, the titanium atom, you can think of it as actually getting somewhat dislodged from its position in the center in this tetragonal structure, and then that ends up creating an electric dipole. Now, dipoles, if you attended one of our previous webinars about MLCCs, dipoles are critical to the operation of capacitors. It is these dipoles that actually allow capacitors to be capacitors, as opposed to straight up insulators that don't really have the internal creation of these dipoles. So these dipoles are very important, especially when it comes to class 2 and 3 ceramic capacitors, because of that titanium atom that is displaced from the center of that face center qubit structure. This creates these microcrystal domains of similarly aligned crystals of this tetragonal structure with the titanium atom displaced. And as you will start to apply voltage to it, some of the crystalline domains actually get locked into place with the electric field, and those domains that get locked into place with the electric field, with the applied electric field, are actually not available to act as part of the capacitor. So the more voltage you apply, the more of these domains that you lock into place with the electric field, and the less of these domains that you have available to act as part of the capacitor, which is what causes class 2 and 3 ceramic capacitors to lose capacitance as you apply voltage. So that's what we call the voltage coefficient, or DC bias effect. In some cases, you might hear that referred to as VCC. But internally, that is what's happening. And that, again, all comes from the nature of this barium titanate material, where that titanium atom gets dislodged from the center of that cubic structure. So similarly, what happens is, as I said, you have a lot of these domains unavailable to contribute to the overall capacitance of the device, and this is an effect of the material itself. So you're going to find this happening to varying degrees across all manufacturers. But if you look at there are certain ways to kind of design around or mitigate this effect. So if we look at two capacitors of the same voltage and capacitance, and obviously the same dielectric material, but they're different sizes, what happens is, as I said earlier on, we have multi-layer ceramic capacitors. When you go up in size in an MLCC, you also have a little bit more space between the layers. And as you start adding more dielectric material within the layers, you have more of these domains available to act as part of the capacitor. So here in this case, we're looking at a 1210 and an 805 6.3 volt, 10 microfarad X7R capacitor. That VCC effect is more pronounced in the 805 than in the 1210, because the layers in the 805 capacitor are actually much thinner, right? You have much less dielectric material to act as part of the capacitor, right? Once you start to apply external voltage to it. And because you have less material, you have less of these domains available to act as part of the capacitor and contribute to the overall capacitance. So if you find yourself losing a lot of capacitance with applied voltage, one of the ways you can design around that is, well, to design in a bigger capacitor. Now, I am aware that that's not always an option, so you have a couple of other knobs to turn here, and you can actually design in a capacitor of higher voltage. So to basically try to move that inflection point where capacitance starts to drop off, if you design a capacitor in of higher voltage, this point will actually move out to the right. So if you find yourself in a, let's say in this case, a 5 volt application, you design in a 6.3 volt capacitor thinking you have voltage margin, well, you might not, because if you're operating out here, you're going to lose quite a bit. But if you were to instead design in a 10 microfarad, 10 volt or even 25 volt, by the time you get down to 5 volts applied, you'll probably still you'll have more capacitance left in that case than you did with the 6.3 volt. So that's another way to sort of design around this effect. And finally, you can always just spec out more capacitance. So instead of putting in a 6.3 at 10, you could put in a 6.3 at 22 or even 47, something like that, right? Something more than just 10. If you really need that 805 size and you can't go up. This is unlike C0G. Now C0Gs, because of the way that because of the nature of the material, that calcium zirconate material, it doesn't have those physical dipoles. Now dipoles are still created in C0G material. It's just not by physical means, like in the case of barium titanate. So that means that it has very stable capacitance over applied DC voltage and AC voltage. So really effectively no change at all. And you can actually see that reflected in our KSIM tool. And speaking of our KSIM tool, you can also see this same effect reflected in our KSIM tool. Then another thing that happens with class 2 ceramic capacitors, and this is all nature of the barium titanate material that we use, is this idea of aging. Capacitors actually age over time. So from the first time it's fired out of our kilns and the capacitor is essentially done and complete, at that point, from the last time they saw their Curie temperature, they start to age. So a fresh capacitor, fresh as in freshly fired capacitor, will have a certain amount of capacitance. And that crystalline structure that I mentioned earlier, that was highly expanded and all that stuff, with the titanium atom pretty well centered into the capacitor, into that face center qubit structure, over time starts to relax and shrink a little bit in size, if you will, and dislodge that titanium atom. And that continues to happen over time after the capacitor's been fired. Now, that doesn't mean that if you have a capacitor sitting on the shelf for a long time, it's essentially worn out and worthless. Often reflow temperatures that we use for our circuit board manufacturing are well above the Curie point. So once you place it on the board, send it through reflow, that kind of resets the time a little bit for these class 2 and 3 ceramic capacitors. And the effect is actually fairly minute. It's depends on the capacitor and the type and all that stuff, but it's a couple of percent, 1.2, 3% per decade hour. So after 10,000 decade hours, you may have lost 6% or 9% of your total ceramic capacitor. So it's a decade hour thing, and the effect is a lot more pronounced in the first 100 hours than it is in the next 100,000 hours. And again, because class 1 ceramic capacitors are made with a different material that doesn't have this mechanical dipoles that are built in, they don't have any aging effect whatsoever. And once again, the last effect we'll talk about is this piezoelectric effect. And many of us who have designed circuits, we see and have actually literally heard as we apply switching voltage to ceramic capacitors, a buzzing or even a clicking sound. And that is an effect due to that titanium atom, that as you start to apply voltage to it, as I said, it gets dislodged from the center of that face-centered cubic structure, and it mechanically distorts the shape, in a very minute sense, mechanically distorts the shape of the capacitor. And that distortion, if you hit the right resonance point, can actually couple onto your PCB, and the entire PCB acts like a sound generator. So you can, if you have some electronics that you hear this low whine or buzzing from, some of that might come from your class 2 ceramic capacitors. And sometimes we have to design around that effect, especially in consumer electronic devices. So this is the effect I was telling you, that as the capacitor is starting to vibrate, it actually may couple onto the PCB, and you can hear audible noise. So with that, that brings me to the end, and now I'll open it up for some Q&A. I see I already have one question came in. So the first question that came in was, does KEMET have any method for users to de-age their class 2 or class 3 ceramic capacitors? Special considerations if the capacitors are in tape and reel when de-aging. De-aging in tape and reel. I would have to get back to you on that. I don't know of any situations where, at least personally, situations where people have asked to de-age their capacitors in tape and reel. Normally, we just kind of say a little bit of, don't worry about it, it'll all go back to normal as soon as you place it on a PCB and send it to reflow. But as far as de-aging in tape and reel, I haven't heard anything. I don't know off the top of my head if we have recommendations for that. But we could get back to you on that. So we had another question come in. What about the ESR of class with, I think maybe missed, okay, might have missed might be a typo there. What about the ESR of class capacitors with DC voltage? Oh, class 2 capacitors with DC voltage polarization. I'm not sure what you mean by DC voltage polarization, as in permanently polarized due to DC voltage? Not sure. Maybe we can clarify that later. Let's see. There's a question here: how to mitigate the piezoelectric noise in component selection and designs? So piezoelectric noise, some of the ways to design around that is kind of an escalation of matters. So the first attempt is to perhaps move it to a different spot on the board. Also use different capacitors. As I mentioned earlier, that sort of DC bias, that piezoelectric effect is more pronounced, especially with some of the smaller capacitors. So one attempt you could do is maybe design in something bigger. Lead frames, not always an attractive option, but that helps to decouple the ceramic body a little bit from the PCB itself. I've heard of soft terminations, flexible terminations also helping to mitigate that effect. So it just becomes an escalation of matters. So back to permanently polarized class 2 ceramic capacitors. I have to admit, I'm not entirely sure about that. I'll kind of put it in my notes here as a follow-up. But permanent polarization is not something I'm aware of. I'll have to look into that. I'm sorry. Is PME DC bias performance better than BME? Not to my knowledge, because it's a factor of the material itself. So I'm not aware of PME necessarily being better than BME. Now, if you think about PME capacitors, they tend to be a little bigger because it's kind of older technology. So if you think about it that way, then yeah, the DC bias will be better because of the effects that I mentioned earlier. As you get bigger, you have more separation, you have more material, dielectric material between the layers, and the performance is better. But I was kind of thinking in a straight apples to apples comparison. Same size, same cap, same volt, PME/BME, I don't think it would necessarily be better. So this kind of touches on that same one. Does PME or BME electrodes age faster? The aging effect really doesn't have much to do with the electrode materials, more the ceramic material itself. I'm gonna have to be selective with some questions here. Is it suitable to use MLCCs over the self-resonant frequency? That all depends on what you're doing with it. So in something like a pi network, where you're really trying to manipulate certain parts of that impedance curve, then I would say it's fair to use above self-resonant frequency if you really want, if you're trying to get into that inductive region. However, if you're doing something like the output of a DC to DC regulator, 400, 500 kilohertz, 1.5 megahertz, something like that, I wouldn't recommend using above self-resonant frequency, because at that point, it's no longer really a capacitor. And I try to paint this picture to some people, right? If you're an electron traveling down a circuit, of course, it doesn't really work like that. And you're coming in at a certain frequency and you encounter a capacitor, but you're at a frequency that capacitor is above, you'd be above the self-resonant frequency of that capacitor. To that electric, to that electron, you're not really a capacitor, you're more of an inductor. So totally a elementary type of analogy, but that's how I try to see it. Oh, this is a good question. So why is class 2 not suitable for AC applications? This is a fantastic question. What happens in the case of AC applications for class 2 is we got to think back to those dipoles. Those dipoles and the fact that you're kind of mechanically almost moving the dipoles. AC applications, and we're talking like mains and stuff like that, those AC applications are slow enough that they would cause a dipole to totally switch polarity directly from one side to the other. And you get heating in the domain walls between two domains. And almost think of it like friction, as these domains are switching back and forth, rubbing up against one another. And that heating can actually get very quick and very high, and eventually crack the ceramic capacitor, will shatter like a broken plate. We actually have some pictures of that, and it's pretty dramatic. Let's see, just really quick, hand soldering instead of reflow. Will hand soldering provide sufficient time and temperature to achieve de-aging of class 2-3? I don't think so. And actually, I'm not going to say we don't recommend hand soldering. I hand solder all the time. If you're hand soldering with a soldering iron, you might cause some differential heating and coefficient of thermal expansion mismatch from one side of the capacitor to the other, and that thermal shock might actually crack and start to delaminate the capacitor. Hand soldering with a heat gun, maybe. It just depends on how long you've applied it. But usually, like I said, what we say is just reflow oven, that should settle. All right. I think we've got time for one more question. And this is a good one. All right. Do you know about the characteristics of PLZT ceramic capacitors? So lead, lanthanum, zirconate, titanate. So a little bit, yes. We don't make PLZT MLCCs. That was a lot of letters. But when it comes from a characteristic standpoint, that's an interesting material that when you apply a DC bias to it, the capacitance actually goes up for a while. Not like class 2s and 3s. In class 2s and 3s, let me go back to that slide. In barium titanate ceramic capacitors, the capacitance will go up slightly as you start to apply voltage and then eventually drops off. In the case of PLZT, it actually goes up and stays up for a little while. Now, that material, obviously, that would be favorable for some applications like perhaps some DC links and things like that. But obviously being lead, not Rojas compliant, and mechanically, they're not as robust. There's actually quite a bit of mechanical analysis done to it. And I think it's the bulk modulus of the PLZT material that's much less than class 1s or other types of materials that mechanically make it less sound than the normal ones. And because of that, you have to apply lead frames to it and things like that. So sometimes it works. It all kind of depends on your design. But that's about as far as I know of PLZT. And that's the fact that PLZT goes up as the capacitance goes up as you start to apply voltage to it can make it attractive for some applications. All right. I think that's all the time we really have for questions. If you have any other questions, I know I didn't get to them all. We'll keep a record of these and we'll try to get back to as many of these as we can. And if you have any others that come to mind, you can submit them through the Contact Us form of this webinar page, or reach out to me directly. I guess maybe I can add my contact info on here real quick. So you can reach me at and we'll send out these slides so that you have this material. But as I said, if you haven't, we'll close it out here. And if you have any further questions, please reach out to me or use the Contact Us form for this webinar. So thank you very much for joining, and we'll see you at a future webinar.